Hello. Today we want to talk about the Carleman's inequality, which says that for a given sequence, if we sum up the products of the first k terms of the sequence to the power of 1 over k, that is smaller or equal to e times the summation of the sequence, where e is the natural number. So this inequality is specifically interesting because of its proof. I find it has an interesting trick that is worth talking about. So let's get started. Let's start out with the left-hand side, which we have a summation from 1 to infinity. Let's actually write down the k from 1 to infinity of a1, 2 to ak to the power of 1 over k, and that's smaller or equal. Oh no, actually we don't want to estimate just yet. First, we want to introduce new factors to this term. So let's write it out. We have the summation k from 1 to infinity, and now instead of writing a1, a2, we write a1, c1, a2, c2, and so forth till ak, ck. To the power of 1 over k. And we can do this as long as we divide them again away. So c1, c2 till ck to the power of 1 over k. So these are the terms that we introduced, c1, c2 till ck. And of course we can do that as long as these k's are positive numbers. That we can just multiply them in and then divide them out again. At first glance, it seems very arbitrarily, this trick, but you will see why it's a very interesting tool to use to make estimations. Now let's let's use the AMGM inequality now. This is smaller or equal to the summation k equals 1 to infinity, and specifically on these denominators, on the denominator, 1 over k times a1, a1, c1 summed up until ak, ck to the power. Oh no, there's no power anymore. We already used the AMGM inequality over this, divided by the term c1, c2, ck to the power of 1 over k. Now let's write out the summation in a short form. This is the same thing as the summation from k equals 1 to infinity. And this is just 1 over k times the summation of ai, ci, where I goes from 1 to k. And all of this has to be, of course, divided by these other terms, c1, c2, ck divided by k, 1 over k. Let's write this out further. So this is 1 to infinity, and then there is some the I from 1 to k, 1 over k times ai, ci divided by c1, c2, and so forth to ck to the power of 1 over k. Okay, what we want to do now is to change the order of the summation. And if we want to do that, we have to consider a few things. So let's take a look at the way we are summing right now. So we take a look at this grid. We start out with k, and then so our x is k, and then our y axis is I. Let's say k is 1. Then if you take a look at the summation above, our I can go from 1 to k. This means we get 1 point for I, which is like this one. So also write out the other. Okay, let's move forward to k equals 2. In that case, I runs from 1, so I can get 1, and it also can get 2 because it sums up until k. If k equals 3, then our I runs from 1, 2, and 3. Okay, so what we want to do now is we have to what we have right now is k from 1 to infinity, and then I from 1 to k. So of course this goes to infinity. And the term inside. The term inside doesn't really matter that much for us right now. What we want is that we want to have the I on the outside and k on the inside. So we have to see what the starting points and what the end points are in this case. Okay, so if I equals 1, then k runs from this 1 and then up until infinity, right? Okay, let's take a look at the second point for I. If I equals 2, now k does not start at 1. It cannot start at 1 because remember, no matter the order of these summations that we choose, we want to capture the same points, the same indices that we insert into our term. So k cannot start at 1. K has to start at 2, at exactly the same place where I started. So this is then our k. If I starts at 3, then now k cannot start neither at 1 nor at 2. It has to start at 3. It has to start exactly where I was determined. So I goes from 1, 2, 3 up until infinity. So we have from 1 to infinity. And then k, and we have the condition that k has to start from I to infinity. We cannot start from just any point, as we have just argued here, that these points must be missing because we want to have the same red points, the same indices. And of course, it's not bounded on the right side. It goes to infinity. Thus, we have the upper bound non-existent. It goes to infinity. Okay. So this is a bit complicated when you take a look at it, when it's the first time you look at it. But when you just repeat it over and over and over again, it becomes more clear. Let's use that for our case. So this is just like a thought that is often used without really mentioning why this change of summation was done. So we go from I equals 1 to infinity, and then our k goes from I to infinity. And then we write the same term, of course, again, 1 over k times ai ci divided by c1 to ck to the power of 1 over k. Okay, so we see that these ai ci's do not depend on the inner summation. We can just drag them out. We have from 1 to infinity. Then we have ai ci times the summation of 1 over k, 1 over c1 to ck to the power of 1 over k. And so k goes from 1 to infinity. And now we see why we introduced these ci's to begin with. What we want to have is the following. We want to have this summation here. Summation of 1 over k times k plus 1 from 1 to infinity. Because this summation, if you use the partial decomposition, you see that this is just the same thing as 1 over k minus 1 over k plus 1. Partial fraction decomposition, it's called. And after that, we use the telescoping trick to see that this is just... actually, I made a mistake here. This starts out at I and not at 1. So this is your k from I. And this gives us 1 over I, because all of the other terms will get cancelled. Think about it. Let's just maybe draw it out. 1 over I minus 1 over I plus 1, and then plus the next pair. That's 1 I plus 1 minus 1 I plus 2. So these are just like the different pairs where we run the index over and so forth. So all of these terms will get cancelled except the first one. And that's why we get this 1 over I. And we would like to have this kind of situation. Now, to impose this condition, we could just enforce it and say, okay, we define 1 over C1, C2, CK to the power of 1 over K to be equal to 1 over K plus 1. So we can do this because these CIs are all unknown. This makes this trick so interesting. These CIs are unknown. As long as they are positive, we can do these kinds of conditions and definitions. So why did we do these definitions? Well, because if we define this thing here as K plus 1, well, then we have exactly what we wanted. It's just the summation of 1 over K and 1 over K plus 1. And if we do this, then we get our result, which is then 1 over I. Okay. Let's write it out. So we have now continuing the summation, which is I from 1 to infinity, and then the summation of K. Oh, no, we have something in between. We have these IIs and CIs. So AI, CI, summation from K equals I to infinity of 1 over K times 1 over C1, C2 till CK to the power of 1 over K. And this one is going to become 1 over K plus 1. Now we have the summation from I equals 1 to infinity of AI ci summation of k from I to infinity 1 over k times 1 over k plus 1. And this is because we already established that this here becomes 1 over I. Then we have the summation of I from 1 to infinity and AI ci over I. Great. But we still have a problem. We don't know what these CIs individually are. We know what they are collectively if we have 1 over these terms. So how can we calculate that? We can actually infer this. If we have 1 over C1 to CK over 1 over K, if this is equal to 1 over K plus 1, which we conditioned, then we get C1 till CK equal to K plus 1 to the power of K. And of course, this is true for any kind of index that we want to do. So then we also have, let's write this equation. Let's give it like this mark. Now the next step is to use this equation for k minus 1. So now we have C1 until CK minus 1. So now we have a different index, but it's the same equation. This is now k instead of k plus 1 to the power of k minus 1. Okay, why do we even do this? Because we want to write out this CK as C1 multiplied until CK divided by C1 multiplied until CK minus 1. Because all of these different terms, they get cancelled and we only stay with CK. But we know what these two different products are. We have here k plus 1 to the power of k, and here we have k to the power of k minus 1. Let's pull this k to the power of minus 1 out, and this becomes k times k plus 1 to the power of k divided by k to the power of k. And this is the same thing as k times 1 plus 1 over k to the power of k. Great, so we have now our term for these CKs that we can insert into our summation. So this is the latest state of our summation. Summation from I equals 1 to infinity of AI times CI divided by I. Let's write it out here. So summation of I to 1 to infinity of AI CI divided by I. We already established what these CIs are. AI and CI, as we said, is I times 1 plus 1 over I to the power of I divided by I. And this gets cancelled, and now we have summation 1 to infinity of AI times 1 plus 1 over I to the power of I. So what do we have so far? This is the summation of A1 till AK to the power of 1 over K from 1 to infinity is smaller or equal to the summation from 1 to infinity. Actually, we can now just say that it's the same. We only have one index, so we can just say that and use the K as an index. AK times 1 plus 1 over K to the power of K. This is even stronger than what we wanted to show. We wanted to show the Carleman's inequality, which had like an E here on the outside, and this here non-existent. But this is even stronger. So, but let's derive the inequality now. We know that that 1 plus x is smaller or equal to e to the power of x. And now, if we insert into this x 1 over k, then we get 1 plus 1 over k smaller or equal to e to the power of 1 over k. Now we potentiate the inequality with k, and then we have 1 plus 1 over k to the power of k smaller or equal to e. That's great. Now we can estimate this thing here and say that's smaller or equal to e, and then we get our desired inequality. smaller equal to e to the times the summation of these ak's. Yeah, and that gives us our Carleman's inequality.